we'll take our quick look at the calendar. Today, September 15. It's our introduction to derivative formulas. Today's class activity, I think, is on the shorter side. So I think it was a good day to have the peer tutoring description come in. And I actually think that the very next class is on the longer side. So we might steal a little bit of the end of today's class to start the longer class scheduled for Wednesday. Here's something that I don't think I have talked about in this class, but coming up on Friday, there's two things happening. Quiz, which I have talked about in this class, but the project check-in day, which I don't believe I've mentioned in this class, that is a day on which I have no agenda. There's no new material that we're covering. There's no extra homework assignment. It is just 1 hour and 10 minutes for you guys to work with each other and or with me on either or both of the two projects. And in each of the three segments of the class, you know, the tests kind of separate the course into thirds roughly. There is a project check-in day scheduled, all right? So in order to take most advantage of that 70 minutes that you will have on Friday to just work with each other, you're going to want to get as far as possible into one or both of those projects as you can by Friday. My guess is that in that 70-minute block, if you use the time efficiently, maybe you'll be able to do like a quarter of one of the projects, or maybe even a little bit more. I don't know. But I think it's going to be like a quarter regardless of where you are. So if you haven't started the projects, then you're going to get the first quarter done, which is great. But the problem is that's the easiest part of the project. If you make your way and follow the timeline that we mentioned, then the quarter of the project that you'll be working on will be in the harder section of the project. And so that's why I think it's a good idea to get as far as you can as possible before Friday. Any questions on the schedule? Okay, so let's jump in on, I think we said page 28, is that right? 38, page 38, and we'll start with the demo at the top. Can we go to Kyle? Sorry, Tyler. Can you read the summary? Yes, please. Thank you. All right. So the demo starts with something about notation. It says we'll see this notation in a few classes, but that d over dx and then the bracket is just going to mean the derivative of whatever is inside the bracket. So we'll have more practice with it soon enough, but you see that and it just means the derivative of. Just like this symbol means, how would you read this out loud? The square root of, right? And then you'd be looking for what number is inside. So that means the derivative of whatever's inside. Okay, our very first rule. If c is a constant, then the derivative of c is 0. In plain English, the derivative of a constant is 0. The derivative of any constant is 0. So for example, in number 2, when I ask you to find the derivative of -7, what's the answer? 0. The easiest derivatives to find. Derivative of any constant is 0. Number 3 is something called the power rule, which we actually saw briefly last class. And here it is in symbols. It says the derivative of x to the n, where n is a number. Right? The variable is downstairs, but the derivative of x to the n is n times x to the n minus 1. So in English, when you want to take the derivative of x to a power, you bring the power down, you copy the x, so the n comes down in the front, you copy the x, and you subtract 1 from the power. Bring the power down, copy the x, and subtract 1 from the power. So in number 4, it says find the derivative of x to the 6th. So what comes down in the front? 6. What gets copied? X. And then the new power is 1 less than the old power. So what's the new power? 5. 6x to the 5th. Okay, so let's take a step back for just a moment. Up until this moment right here, finding the derivative of x to the 6th would have been a very time-consuming, very lengthy algebra problem, starting with that big old formula, limit as h goes to 0, f of x plus h minus f of x over h. And then you got to do all this expanding and maybe some factoring or maybe some rationalizing. You guys remember these were long problems, right? So the idea about today is that it turns out there are little shortcuts. And from this point on, we're going to be using these little shortcuts to find our derivatives, right? Except for maybe one problem on the quiz and one problem on the test. But the idea is that we're going to use these shortcuts to find derivatives much more quickly. Raise your hand if before today's class and before you read the reading for today, you already knew this power rule. You knew the derivative of x to the 6th. Yeah, a few folks. And so I know that there's different amounts of calculus that we've seen in this room before this semester, ranging from none to like maybe a full semester or like a high school AP calculus course. And so some of you have like an inside track into these rules. And if you're going to remember something from your past calculus experience, it's probably going to be the rules we're covering today. So when you're doing the activity, if your neighbor is just flying through and you're sitting here thinking, okay, which one comes down, and are we adding one, are we subtracting one? It's quite possible that the person sitting next to you has a lot of experience with this already. So give yourself time as you work through these new rules if you've never seen them. Next one, derivative of x to the negative 4. What comes down? Negative 4. What gets copied? X. Subtract 1 from the power? Negative 5. It's really easy to go the wrong way if the power is negative. You subtract 1 from that power every time. And then the last one is the derivative of the cube root of x to the 5th. Yeah, the rule that we just cited only works for x to a power. In this case, we need to do some rewriting before it looks like x to a power. So I'm going to copy this new, possibly completely unfamiliar symbol for you, the derivative of, and then I'm just going to rewrite what's inside. Cube root of x to the 5th is really x to some power. Do you guys remember? Is it 5/3? Is it 3/5? Yeah. So this is something maybe you just know, and then from that maybe you can piece together, oh, there's an invisible 2 here, and there's an invisible 1 there. So you just have to know where the pieces go. So this is x to the 5/3. And now it looks like x to a power, so I can use my brand new rule. So what comes down? 5/3. What gets copied? X. Carefully subtract 1 from that power. 2/3 is right. Any questions on the power rule? Okay, number 5. If c is a constant, then the derivative of that constant times a function f of x is equal to the constant times the derivative of the function. What that says is that if you see a constant in front of something that you know how to take the derivative of, you can basically ignore the constant, just copy it down, and then take the derivative of that function and multiply at the end. So here, this first thing in bold, constant multiples come outside the derivative and get multiplied after you take the derivative. And then a special case over here on the right says the derivative of c times x is just c, because, well, we'll just leave it there. It's just c. Okay, so let's see if we can do 6 both parts here. So the idea with this one is that that negative 2 can just sit there waiting for you to take the derivative of x to the 5th. Negative 2 times basically just gets copied. And now we already know how to take the derivative of x to the 5th. What comes down? 5 comes down, copy the x, 4th power. See it? The negative 2 shouldn't bother you. Just this new rule that says constant multiple, you just copy it, multiply at the end. And then, of course, we would want you to mush together those two numbers, negative 10x to the 4. Okay, and then the derivative of negative 24x, we're in this special case over here. The derivative of a constant times x is just the constant, negative 24. Okay, number 7. So that's for any constant, let's find the derivative of c over x. All right, just to save time, I'm just going to write the answer. So the way that you would do this would be to bring that x upstairs and rewrite it as a negative 1 power, right? X to the first on the bottom is x to the negative first on top. And then you would do your power rule and then just simplify it a little bit. We're just going to jump to the answer. It's this, negative c over x squared. And so if we want a rule in English for the derivative of a constant over x, it's negative constant over x squared. So let's try that. 2 examples down here in number 9. Okay, to find the derivative of 3 over x, we say, oh, this is one of these special things. It's a constant over x. And the answer is just negative the constant over x squared. So what goes on top? Negative 3 over x squared. Easy. The next example, slight change. It's a new variable. The variable is t. You'll also notice there's a dt on the bottom. It had been a dx the whole time. We'll talk about the notation formally in a couple of classes. But it's the same idea. A constant over x, or t, it's the same rule. So what goes upstairs? Positive 5, right? It's the negative of the constant divided by t squared. Here's the deal. You don't need to memorize that one. You're going to memorize a bunch of rules on this page. You don't need that one, as long as you're willing to go through the trouble of first rewriting it as a constant times x to the negative 1, then taking the derivative, c times negative 1, x to the negative 2, and then finally putting that x to the negative 2 back downstairs. But personally, I have found it very advantageous to just memorize this as a separate rule. It comes up so often, and I don't feel like doing that same calculation over and over again. Next page starts with a couple of rules that look really complicated, but they're quite nice actually. We'll look just at the first one. It says the derivative of the sum of two functions is really the sum of the derivatives of the two functions separated. So this says when you're going to take a derivative of a sum, you can just completely separate the two functions, take their derivatives individually, and then add them up at the end. So let's take a look at 11. It says find the derivative of this function, and then we'll find the equation of a tangent line. So first, good notation. How do I write the derivative with f of x? So we're not going to do the d over dx. We're going to do the one that has the f of x notation in it. F prime of x. Okay, good. Okay, so now we're going to take our derivative. What do we do with that negative 5? We leave it. We copy it. Negative 5 times. And now the derivative of x to the 4th, we know what comes down. 4 x to the 3. Good. And then here's the new rule, plus. Because when you take a derivative of a sum, you're just doing them separately and then adding them at the end. Next part is 7x squared. What happens with 7? Stays right there, times. The derivative of x squared is 2x to the 1st. You don't need to write the 1, but I'm just getting practice with this new formula. Next one, minus 3x. That was one of our special cases. The derivative of a constant times x is the constant. So what's the derivative of negative 3x? Negative 3. And then finally 2 cubed. So what comes down? 3 comes down times 2 to the 2nd. No, that's not right. What is 2 cubed? 8. What's the derivative of 8? 0. Derivative of any constant is 0. So don't be fooled. Just because it looks like a power doesn't mean you can check your brain at the door and start doing that power rule. The derivative of 2 cubed is 0. Okay? All right, so let's just clean this up a tiny bit. So that becomes negative 20x cubed plus 14x minus 3. Okay, so that's the answer to the first part. There's the derivative of f. And now we're going to find the equation of our first tangent line. And the point that we're interested in is x equals 2. Forget about the fact that it's a tangent line, but just any old line. If you want to find the equation of any line, you usually need 2 pieces of information. Slope, y-intercept if we're really lucky. If not, any point will do. right? Slope and any point. Okay, so let's get those two things. So any point and the slope. Okay, so any point. I know what x is. What's the x that we're interested in? Is 2. But I'm not given the y. So how do you find the y for this tangent line? I don't really know anything about the tangent line. You know, this is some quartic function, so I'm not going to draw that one. I'm just going to get a very rough sketch here of some quartic looking thing, right? And then x equals 2 is right here. And so the tangent line maybe is something like that. It's all rough and has very little to do with the exact picture for this function. How would you find the y coordinate of that point? Plug it into what? Into the original equation, into the f equation. The point is on the tangent line, but it's also on the curve. And if you want to find the y for the curve, you just plug it into the original. So right in here, we need to put f of 2. Okay, can somebody do that calculation and then we'll get it in a moment. And while we're waiting on a calculation, we'll move on to the slope. The slope of that green line, the slope of the tangent line, that's a calculus thing. What is the slope of the tangent line? What do we call it in calculus? The derivative, right? Because remember we said the derivative is slope of the tangent line. So when I want to find the slope of the tangent line, I translate in my head, oh, it's just the derivative. But it's not the derivative that's written up here in blue. It's not f prime of x, which is an entire collection of derivatives. It's the derivative at what x value? At 2. I want the slope of that tangent line, not the slope of any of these other tangent lines that are out here. I just want this one. So we need to find what? How do I find the slope at 2? F prime of 2. That is what we are finding. Okay. So 105 says Andy. If anybody can confirm that, that would be super. Anybody have F of 2? Negative 50. Anybody confirm that? Okay. So maybe we'll just wait on one confirmation for the 105. And in the meantime, let's just move on. So I just want to point out, we had to find F of 2. So I'll put that up here, negative 50. So we had to find F of 2 because we wanted the y value at the point. We had to find F prime of 2 because we wanted to find the slope of that line. And then we just put them together. So the equation of any line, well, there are a few different forms. I'm guessing most of you use the mx plus b form. So that's the one that we'll use here. What's the y coordinate? Negative 50 is the only y coordinate we have, right? What's the m? 105, that's the slope of 135. Can anybody confirm 135? Negative 135. Just in the nick of time. Okay, so slope is now negative 135. What's the only x coordinate we have? 2. What's the b? I don't know. That's what we're trying to find out. Everybody see where the numbers came from for that equation? Just plug everything in so that we can find the b. Okay, so what does that become? Negative 50 equals negative 270 plus b. So b is equal to 220. So that means that our final equation of the tangent line, y equals, okay, m, I still need a number there. What's the slope? Negative 135 times x plus, what's the b? 220. That's the equation of the tangent line. The slope is just a number. Yeah, that's the equation of the tangent line. Okay, so I don't need you to follow along, but you're going to do this in the activity. So I wanted to do it once here in front of you. So I'm going to graph both the original equation and the tangent line. minus 2x, oops, minus 2x, and then plus, I'll just write it as 8. Okay, so there's the original. And then down here, we're going to graph the equation that we just found, negative 135x plus 220. Now, I'm going to think a little bit before I hit graph. I want to talk about the window. Everybody okay with what we're graphing here? It's two things. Okay, so the window, negative 10 to 10 seems fine. It just needs to include the x equals 2 that we care about. But this y range is not going to help us. Where is this point? What's the y coordinate of the point we're interested in? It's negative 50, so I got to make sure I at least can see down there. So how about we do like negative 100 to 100? You don't need it to be symmetric. Just got to make sure that negative 50 is there. So we're going to see some downward-looking quartic function. There it is. And then the tangent line at x equals 2 should just barely graze the graph. It's hard to know. There's just not a lot of pixels on that window. But I mean, it looked pretty good, right? Like if the line happened to go like here, I would say, well, that's a problem. And if the line didn't touch the curve at all, that's a problem, right? So it seems fine. If you wanted to fiddle with the window, you could hone in a little bit so you could really see that the tangent line just barely grazes against the curve at exactly the right point. Any questions on this process right here? Okay, so group activity follows. Go ahead and get as far as you can. And like I said, I think we're going to come back together for maybe the last 15, 20 minutes of class. All right, so like I said, we're going to steal a little bit of today's class to jump to the material for the next class. I'm not doubling your homework. This homework assignment is not going to be assigned until Wednesday. But let's see if we can tackle a bunch of what's on this page right here. So the daily summary, who was our reader before? Can we go to Wayne for this one? Thank you. Kevin, number 1. Okay, so local max and local min we have not defined, but hopefully just looking at a picture will help us understand. If I asked you to look at this graph and decide if there was a point that was higher than any other point, is there one or is there not one? If this graph continues forever, is there a point that's the highest point? No, I mean, in theory, this graph goes up and to the right forever, right, to infinity. So there's no highest point. That said, there are points which are locally higher than all the nearby points. So for example, this guy right here, it's not the highest point anywhere. There isn't one, but it is higher than all its neighbors, right? And so we're imagining like maybe a chain of mountains. And you've got like all these peaks and valleys, and maybe you want to tackle the very biggest one, but there's something to be said for tackling some of the smaller ones. Each of those smaller peaks is called a local maximum. Even if there's higher peaks around, those points are higher than the nearby points. So that's a local max. So we're going to get the coordinates here. X equals, I'm calling it B. There's no numbers in this problem, it's just letters. So X equals B is where we have a local maximum. Notice we're not saying anything about the Y, it's just the X coordinates we're giving. Where's another local maximum? A point that's higher than the points nearby, it's F. Which really seems like a jip because F is like at sea level and it's not anywhere near as high as the other point we colored in red, but it is higher than the points nearby. Agree? So that is a local maximum. Any other points on this graph that are higher than everybody nearby? J. So if we stop the graph at J, then it would count. But for example, here's a point near J that's higher than J. So there's really nothing special about J. Okay? All right, same idea, but now local minima. These are points that are lower than points that are nearby. So where's the first local minimum? D is good, comma, the next local min, H is good. All right, so we're just looking for local peaks and valleys. All right, let's go to number 2. Petru, can you read 2? Would you guys agree? At all the red points, and I didn't label these, but here they are, at all the blue points, tangent lines are horizontal. Okay, makes sense that that's a good place to go if you're looking for peaks, because when you're at the top of the mountain, everything is flat locally. Okay, let's move to Mike for number 3. Okay, so would you guys agree that that point right there is a local minimum? It's lower than the points nearby, but is the tangent line horizontal there? No, there isn't. Even the tangent line doesn't make sense there. So there's 2 places we're going to look for local maxes and mins. We're going to look for places where the graph is horizontal, the tangent line is horizontal, and we're going to look for places where the function isn't differentiable. Those are the 2 candidates. So number 4, Andy?
We summarize our observations from above in the following theorem, which is from this book. Fermat's theorem. If f has a local max or min at c, then either f prime of c equals 0 or f prime of c does not exist.
Okay, so those are our 2 candidates, either horizontal or not differentiable. Haley, number 5. Okay, so that's our definition of critical number, place where the graph is horizontal or derivative is not defined. All right, moving on to Dan for 6.
Going back to the first graph, this section, identify the x-coordinate on global maximum.
Okay, so a couple of things that are different about this question compared to the first question. First, there is this word global. What word did we have in the first question? Local. And the other thing that's different is that I'm giving you this closed interval between A and J. So let's go back up and take a look at just the parts on the graph between A and J. So that starts right here. I'm going to color all of this stuff in green so that we really focus our attention only on, and then we stop right at J, A to J. Okay? So on that closed interval, is there a global maximum? That is to say, a point that's higher than any other point. Where's the highest point on the green? It's at J, right? Why is J special? Because we chopped the function off at that spot. J, there's nothing special about J other than this like kind of artificial thing that we did where we said the function stops at J. You let it go a little further and J becomes pretty insignificant because there are higher points next to it. But J is where the absolute max is. And where's the absolute min? The lowest point anywhere. D. D is the absolute min. It is lower than any point in green. Right? The special point on the right was J. How come A is not the global min? It doesn't go far enough down, right? There are points that are lower. Okay, so then those are our 2 answers. We said the absolute max or the global max was at J, and the global min was at D. So we'll just write that down here. So the global max is at x equals J, and the global min, x equals D. It's very common to have multiple local maxes, local mins. That's what we had up above. There were like 2 of each, I think. It's also very common to just have one global max. There's just a single point that's higher than anything else out there. It's the highest peak in that chain of mountains. And likewise, just a global min. It's possible you have 2 mountains in that peak that are both exactly the same tallest, but it's pretty unlikely. Okay, moving on to 7. We'll come up here to Isaac. Okay, so that's a process we're going to see repeatedly this semester. But again, thinking about just the green part of this graph. What kind of a point was J, which was the global max? Why was J special? Because we cut it off there. J was an endpoint of our interval. So apparently, endpoints are candidates to be the global max. But what kind of a point was D? It was a place where the graph was flat, which we're now calling a critical number. So places where the derivative is 0 are also good candidates to find the global max and global min. So that's what Isaac just read for us. And like I said, we'll do this procedure a bunch, but here's the first time. Number 8, without using a graph, we're going to find the absolute extrema of that function on the interval 1 to 5. Okay, so let's give this a shot. This is going to be an entirely analytical process we follow because we don't have the benefit of a picture in front of us right now. So apparently, critical numbers are important. So how do we find critical numbers of a function? Figure out where f prime is 0. That's our definition for critical number. It's a place where the derivative is 0 or doesn't exist. So let's take the derivative here. Now that we're experts at our derivative shortcuts, we're going to take a shortcut right now. Normally, I would say, what would we do with that 2? Is we'd keep it, we'd copy it, and then wait around. But how about we just jump to the next answer? We know that that 2 is going to be waiting around for what number to come in the front? 3. And what are we doing with those numbers? We're multiplying them, so we're just going to say 6. X to the 2 is good. And then the same thing happens with the 15x squared. 15 is hanging out waiting for what number? The 2. And they multiply and give negative 30x. Plus 36x, what's the derivative there? It's 36. So that's our derivative. It's something we're going to do over and over this semester is take a derivative and set it equal to 0. Because places where the graph is horizontal are good candidates for maxes and mins. Okay, this equation is kind of messy. It's quadratic, so I guess we could use the quadratic formula. I'm suspecting it factors, but we're going to do something nice to make it easier to recognize. Yeah, let's take that 6 out in the front, right? And now that it's just a 1x squared, it's a whole lot easier for me to think about factoring. Okay, so this becomes x minus 2 and x minus 3. And then we're setting each of these 3 things equal to 0. The 6 doesn't contribute anything. Here we get x equals 2. Here we get x equals 3. What are these 2 things called? They are zeros, but we have a calculus thing that we've just defined. They are critical numbers. New vocabulary word. Takes a little bit of getting used to. Okay, and then the rest of this process just involves, as Isaac read to us, making a table where we plug in endpoints and critical points into the original function f. So the endpoints were given in the problem. What are they? 1 and 5, so they're important numbers artificially, but they're important numbers in this problem. The really important numbers for this function are which ones? 2 and 3. Like those are definitely interesting numbers because that's where the graph is flat. And then all we have to do is plug each of those x's into the original function. Just because we're 20 seconds over, can we split up the work? Just somebody plug in 1, somebody plug in 5, somebody plug in 2, somebody plug in 3. We just need these 4 numbers. All right, who's got what? 23 here. 28. Huh? 55, a workhorse over there. Okay, so we've got those 4 points. If you want to find the global maximum, which one would you say is it? Is it 5? That's right here. Global max. Because the y value is the highest number you see. Where's the global min? Is it x equals 1? Okay, sorry for going over. Next class we'll pick up here, and we'll see you on Wednesday.